example, which I'm not trying to follow. I'm trying to be on time. And also the...
Andreas, microphone.
So where's the microphone?
Yeah, please. It's better for you. It's better for you.
All right.
I think we capture this moment with every presenter. In the microphone. Oh, we missed a lot of it.
Okay. It might have been too loud, I don't know. So yeah, first of all, thank you for the invitation. So far I enjoyed the lunch. I just had a 24-hour flight behind, so this kind of experience if you got stuck in New York, because there's no crew, so that's interesting. The only thing I have to complain is the weather. In Shanghai we have, what is it now, 38, and humidity less than 100, so it's a bit different. I would like to get started with the topic I'm going to talk today, which is not mentioned in my slide. I think it's in the program. So the idea is to give an introduction to what is called Lie group theory. Lie group theory in kinematics. So normally when I talk about this topic in Shanghai, then I get all the attention. Because everybody thinks, oh, a Chinese scientist invented something important for kinematics. Then, unfortunately, I have to say, no, this was a Norwegian. And his name was Lee, and he was, of course, working in good old Germany, inventing something good, right? So, I'm German, so the name is as German as can be, right? Working for a American university in the land of freedom, which is China. Okay, and let's get started with this stuff. So essentially, just briefly about the background. So I actually started with what we call multibody dynamics. So dynamics has to do with forces and this kind of things. But if you want to do it really good, then it comes down to the very basics. And the basic is like motion, right? So it has to do with kinematics. So it turns out that even if you understand about the dynamics, which is, by the way, not easy, then still you have to do something good in kinematics. So I actually came down to, convert, and I'm preaching kinematics. And it's all about things that you know. It's about rigid bodies in the simplest case, and also if you go a bit deeper into the what happens in reality, then it's going to be, it's going to be flexible bodies. Like the human body is a very good, the human as a multibody system is a very good example for a system that comprises, of course, a rigid structure, but has this kind of what we call wobbling masses. Right? Wobbling masses is including, the fat and a bit muscles and all this kind of thing, including the brain. So that makes it very interesting. But even if you stick with rigid body systems, it's quite a challenge. Okay, so just a brief outline of my talk. I tried to, well, at least group it into at least three main groups, which is about the Lie groups in kinematics of rigid bodies. So we are just looking at what has to do with one single rigid body. And then I would like to proceed with a chain of rigid bodies, a kinematic chain, an open kinematic chain. And then proceed going to the closed loop systems, right? So you remember this morning, I guess at least I haven't been here, that there was a talk about closed loop systems, constraints, and so on. Now, you might remember that this was, I guess, a algebraic approach, that you formulated the problem in terms of polynomials, right? If you use this Lie group theory, well, say cosine and sine and this kind of things, then of course you have a different thing. You have an analytic description, right? So the geometry behind the problem becomes a bit different. And then I would like to say something more about any further topics. The point of the good way to begin. The challenge actually of that talk is that if you just call it Lie groups in kinematics, this is an endless topic, of course. And I would just like to give you a bit of an introduction. And this is actually for more or less, the beginner's level, or actually graduate students in the second year kind of thing. But still is interesting. Okay, let's start it. So this is probably the problem that Andreas was mentioning, that part of my slides get cut off. I'm not sure if we can do anything about it. So if you look at what I'm talking about, I would like to talk about the Lie groups, and it turns out in a minute that this essentially has to do with screw theory. And I'm not sure if you, I wasn't here, if you talked about this. Actually, screws, they form an algebra, right, in a sense. So we have this kind of screw product, and this essentially means that we have a certain structure. The structure is essentially defining a Lie algebra, right? And if you then, oh, it's getting smaller. And if you then look at what you can find in the literature, if you try to trace the treatment of this kind of things back, then it goes pretty far back. Actually, it goes very far back. But the first maybe instance where people refer to Lie groups is maybe Chevalier, but also later or even before was Li Yuangshu. And actually, he's a very distinguished professor, retired, of course, from Charlton University. I just met him a few days ago. It's a pleasure talking to him. This paper is from '88, but he started long before, actually. And that paper has an interesting title. It's called Screw Matrix Methods in the Dynamics of Multibody Systems. So at, what is it now, 88, he was actually talking about things that we're talking about today. Combining what we know in kinematics, which is screw theory, with multibody dynamics. And if we talk about multibody dynamics, we're talking about a bit more than just screws. We talk about dynamics, we talk about finite motion, and we talk about the mapping between infinitesimal and so on. And this has to do with Lie groups, right? So in his papers, he mentioned it over the 70s. And it's quite interesting to trace it. So if I would suggest some literature, okay, there's no way of getting it public.
We have to go to the display board and change something.
Okay. Good. So if I was to propose, suggest some literature, I would of course refer to John Selig's book. That's a very nice introduction into, I don't know into what actually. He calls it geometric fundamentals of robotic systems. It's a nice attempt to present what we need in kinematics and robotics in the framework of, I wouldn't say Lie groups, but in terms of a decent mathematical setting. And of course it has to do with Lie groups. The other book that is getting kind of, famous is the one by Muller and Sastry and Lee, which is the thing called the Mathematical Introduction to Robotics, Robotic Manipulation. And they are planning actually a second edition. I'm not sure if this is going to happen. Of course, there are some interesting papers, and if you try to find the first paper that talked about Lie groups, or say Lie group formulation for kinematics of open chains, then you find, of course, the one by Bobov and also Brockett. And the school has to do also with that was Scott Flowen and of course Frank Mark. So, and if you look at the title, coordinate invariant algorithms for the dynamics. For the dynamics, I think there's something more. Then you see that they are already talking about combining kinematics and dynamics. So they have been looking already at the dynamics formulation using Lie groups. Right? So we will see in a few minutes that actually Lie groups are just one way of looking at matrices, because essentially what we are looking at are matrix Lie groups. Right? So, and it boils down more or less to two sets of matrices that are somehow connected by a mapping. This is the exponential mapping. So that's going to kind of, give it the framework. And if you look at multibody dynamics, or say kinematics of systems, then there is this, mostly called matrix methods. And that's just a recent book. There are many books, of course, but there's a recent book by John Eucker and Baran Bhavani. It just came out last year. And I was so surprised when I opened it, because even the notation by I don't know, by coincidence probably, the symbols are the same that we're using in the Lie group settings. It's so interesting that you see that they have been writing exactly the same equations, but not mentioning in one place that you know, we have the Lie group and we have a certain structure behind it. But still they managed to get the same kind of result. This is quite interesting. And one book actually that is kind of been implicitly given an overview, I would not necessarily recommend it, but is the one by Roy Featherstone. Well, not so necessarily recommend it, but it's at least an interesting book. Okay, let's start it. I think there is no way of getting it to normal, right? Well, then just go. So why Lie groups? Well, because the Lie group, you see the term, you know, we have this fashion, right? Any other day there's a new fashion, and currently people tend to use the term Lie groups. I myself, I did the same, but you know, I see that when I talk to people who did never use it before, I get like, you know, people tend to hesitate using that thing. So why Lie groups? Well, Lie groups essentially is a kind of way of looking in a more like general or say holistic way in the matrix approach to kinematics and dynamics. So when we say that it's a kind of holistic or generalized approach, then it means that we have a systematic way of looking at the whole thing. And if there's a systematic way, then what you get is more insight, but also you see some structure behind this, right? And we will see that there is some more structure that you would not find if you just look at the matrices. And it is important that we have this connection to school theory, because essentially what we are looking at is this algebra of schools, and we make a connection of the infinitesimal schools that make an algebra, and this, you know, this group motion of a multibody, which is not an algebra, it's a group, right? And this is what we're talking about all the time. It's a Lie group. And the important thing is that we have some frame invariant properties. So because what we're describing is invariant to the choice of reference. So we have a frame invariant, and in the best case, a coordinate-free description of the kinematics and the dynamics of multibody systems. Okay, let's start with the first one. And that was, maybe try it at least once.
You have to go to the display. It's not changed.
Okay. So, just let me start it. Just look at rotations. I think everybody knows what a rotation is, right? So rotation could be described by a axis. So you fix an axis and you have an angle. So then you rotate the body, right? And then of course you can say, well, if I have one rotation about an axis, call it n1, right? About the angle phi, 1. Then of course I can combine this with the second angle. Okay, so I have the first rotation. I take what comes out, and then I rotate the configuration that comes out of here with about a different axis, n2, and then an angle phi2, and then I get a third angle and a third axis. And of course you know that there is a relation between the two axes and the one axis, and that you can of course symbolically write that there is of course an axis n3 that is giving you the same result as if you take the n1 followed by the n3 axis. What that means is actually that these rotations that form something that is closed with respect to the application of the rotation. That means they form a group, right? Remember, a group is something, it's a set actually, that is closed by the multiplication. We have an identity and we have an inverse. So the identity rotation is of course no rotation, right? The inverse of a rotation is just the rotation about the opposite axis over the negative angle. So we can
Try.
Yeah, that's good. Well, we have 90%, that's good. Right, so we are here. So, but we know something more. So we know that's a group. We know, of course, that rotations do not commute. Right? If I rotate about n1 and then about n2, does not give you the same as if I rotate about n2 and then n1. So we have a non-commutative group. That's good. We have an inverse, of course, which is just the rotation about the negative axis. That's fine. We know something more. We know that there is an invariant subspace. Actually, what we're talking about is that a rotation is actually a transformation, and it's an isometric and orientation preserving transformation of a Euclidean space. So what that actually means is, if it is isometric, what I'm saying is actually, I fix 2 points on that body, right? Whatever happened, whatever the rotation I'm performing, the distance between the 2 rotations, of course, remains, right? This is isometric. The distance does not change. And also we have an orientation preservation property, which means that if I have a right-handed, maybe I fix 3 points, and I make a right-handed coordinate frame, it stays the right-handed coordinate frame. It does not become a left-handed coordinate frame. So this is what it's all about. So, not very interesting maybe, but let's see what we can say. We can of course represent rotations, and you know that we can of course use orthogonal matrices, right? Usually we call them just rotation matrices. And these matrices are the three matrices with a positive determinant, active determinant +1. And they form, of course, because they represent rotations, they form a group, because the rotations form a group, right? So we have again another group. And this is what is normally called a special orthogonal group. And essentially this is one first example for a Lie group. We will see why this is a Lie group later on. So SO3. Remember, SO3 is a special orthogonal group because we have an orthogonal matrix. It is special because it could be orthogonal even if this determinant would be -1. It's a special orthogonal because it's +1, right? So it's just a set of all the matrices that have determinant 1 and are orthogonal. And of course, this is what we know from algebra. This is rotation matrices. These are rotation matrices. The inverse is just the transpose, and of course, there is an action because these matrices, they act on vectors, right? You can either multiply the matrix with a matrix, that's fine. So you have like rotation after rotation. But you can also say that I'm actually applying this rotation matrix to a vector. So I'm rotating the vector, right? So you see we have a group actually that acts on a vector space. So this is one thing that has to do with the Lie groups, because Lie groups are transformation groups. So it transforms one vector in another vector, right? That is one thing that makes a Lie group. And in our case, it takes coordinates from one frame into the coordinates to another frame, right? Maybe from the green, what is it now? No, from the red into the green. Or the other way is saying, I have a vector expressed, a body fixed, say we have a body fixed point, and I express the point coordinate of that body fixed vector in the body fixed coordinate, the red one. Then I'm transforming, of course, the point coordinate in the green one, in the maybe space fixed frame, by just multiplication with the rotation matrix. But we know that there are many other ways of representing rotations, right? What about quaternions? Well, you know that there is this kind of, there's something wrong here. Anyway, there is what we call maybe Hamilton quaternions. I mean, it's attributed to Hamilton, who knows. So, and we represent this normally by using this quaternion units, right, IJK. And they have a certain quaternion, a certain multiplication law. If you square each of them, it's like the complex number, right? You get -1, and if you take I times j times k, you get -1. And if you combine this, then you see that there is a kind of multiplication law that if you take I times j, you get k. If you take j times k, you get I, and so on. Okay, and this defines something. Not yet a group, but at least something. That is interesting. At least there is an addition. And the addition is this component wise, right? You add two quaternions and do this component wise. Then there's something that is called a multiplication, right? So you know how to combine quaternions. For whatever reason, it looks like this. And you come, actually, if you use the 4 vector representation, I mean the 4 components, if you put all the 4 components in a vector, so you have the scalar and you have the vector part, then you know that we can actually express the multiplication in this form, right? So the scalar part is just up to here. It's the inner product of the vector part subtracted from the product of the scalar part. And then we have this mixed part here, and this is what you know. So, fine. These are quaternions. And you might know that, of course, quaternions represent rotations again. So, I've said rotations form a group. If the quaternions are somehow equivalent to rotations because they describe rotations, then they should form a group, right? So, there should be a group that is actually related to the quaternions. Okay, we have of course we have a conjugate, this is what we know, and we have of course the norm or the whatever. So, the quaternions do form a group, and this is sometimes called the unit quaternion groups, sometimes, symbolized with an H. Maybe it's attributed to Hamilton. We have what? We have an identity, of course, because just the 1 is the identity, the scalar 1. Then we have inverse, taking the conjugate as an inverse. It's associative, and we have that is important, the closet. The system is closed with respect to the multiplication. If you look at the unit quaternion, right? So we have seen that we have then two representations of rotations. One is the special Euclidean group, that means like rotation matrices, and the other is the Hamilton quaternions. Just two representations of rotations. And both, this comes now with, this is the next step actually, what makes the Lie group, is that we can introduce some parameters, like angles and axes, right? Or angle axis, which has 3 angles or something like that. And this means that we have a smooth parameterization of the groups. And this is what makes a Lie group. Because a Lie group is a manifold. When I'm saying a manifold is something like that is somehow, it's possible to introduce smooth parameters, like angles or, like a chart on a surface, right? Like a smooth surface is a manifold. Why? Because you can introduce a chart, a local chart, and everything is fine. You have local parameters, everything is differentiable, it's smooth. So, and now if this group is itself a manifold, so we can introduce more parameters that are kind of continuously differentiable. And if G is a group, and if the multiplication exists, and the inverse exists, and is again smooth, then this is a Lie group. Well, this is the abstract definition. But if you look at the rotations, for example, it's clear that it's a Lie group because we can introduce parameters. The parameterization is differentiable. There's an inverse, and what else? And there's an identity, and of course we have some sort of associativity. Fine. Are there any other kind of good examples for Lie groups? What about the vector space, our n? If you take the n-dimensional vector space, that actually is a Lie group. Because we have a group multiplication, which in this case is just the addition of vectors. And of course the rotation group is not commutative, whereas the vector space is commutative. So now there is one thing that is interesting. We have seen the quaternions. What is the difference between the quaternions? I mean, the main difference that is obvious. The main difference between the quaternions so far and the rotation matrices is that the rotation matrices, well, this is what the name says, are matrices, whereas the quaternions are not matrices. So if you want, for example, to implement the quaternion multiplication, then you have to do it certainly in a different way than you implement, as far as we have been showing it, as you would do for the rotation matrices. Now there's an interesting theory that goes back to Addo, and this says that any finite dimensional Lie group can be represented as a matrix. And that's interesting, because also the quaternions can be represented as matrices, right? So you see what I'm after actually. I want to have my matrices, because I would like to have everything expressed in terms of matrices. And just as an example, look at Rn. The Rn, the vector space Rn, with the addition, is a Lie group, as I was saying, because we have inverse, everything is very simple. But you can represent a vector in Rn as actually, this is not correct, it should be n plus 1 matrices. So you have this n plus 1 matrix, where you have the identity matrix. So you have an n vector, right? We are talking about n vectors in Rn. you take a vector u, component 1 to n. So you put this into this matrix, right? So you have the common vector here. Then you have the nn identity matrix, and then you put the 1 in here. If you multiply these two, if you take two of them, right? The one here, like here. So if you take u1 and u2, essentially what you get is you get, of course, the identity is 0, 1, and then you get here u1 plus u2. So it's a different way of, maybe a bit complicated way of representing the addition of two vectors. So you see, this is one thing, one example that you, for example, can represent Rn as matrix group, right? Okay, good. What about now with kinematics? So far, there wasn't so much kinematics in here. What we are going to do is to deal with the special rotating order group first, because we are looking at rotations, right? And then we, of course, look at the full rigid body, because the rigid body motion has to do with translation and rotation, right? And not only the rotation. So, and we are going to look at what is normally known as homogeneous transformation groups, right? What happened? Batteries? It must be Chinese battery.
The battery is right there in the graph. Down below, all the way to that.
Back to normal. Okay, so I was actually saying that to capture the full kinematics of rigid body, of course, we have to look at the rotation plus the translation, right? So slowly coming to a bit more of a kinematic viewpoint. Okay, let us look at what happened if we, for example, in a rigid body. So we have that interesting rigid body. Normally these are parallel lines. If I'm not mistaken, this is not parallel. The projector is interesting. So let's say that we have a rigid body, and we have a fixed coordinate frame on a rigid body, right? The red one is fixed to the rigid body, and we have a space fixed. Could be space fixed? Maybe not. What is important is the relative motion, okay? So of course what we have a displacement vector r, and we have a rotation matrix, capital R, right? So what happens then, of course, if you have a point described, a fixed point on the body described in the body fixed frame, and we call the vector q. What happens then if we want to express this same point in the space fixed frame? Of course, you know what is going to happen. You have this kind of transformation, right? So you have, of course, you have to transform the vector q, because the vector q is represented in the body fixed frame, into the space fixed frame. So you have to rotate it. That makes the rotation matrix R. And then, of course, you have to add the displacement of the origin of that body fixed frame, and altogether gives you the point coordinate P. Not very exciting, and you know probably that this can be represented in terms of homogeneous coordinate by just taking the vector, appending it with a 1, so you have a 4 vector, and then we can actually represent the transformation of these homogeneous point coordinates by these 4 matrices, right? So we have the rotation matrix, we have the position vector R, and we have a 0 vector and the 1. And this is normally, you find the name homogeneous transformation matrices, which is not correct, because the matrix is by no means anywhere homogeneous, but this is what you find normally in the literature. The only thing that is, for some reason, homogeneous is the vector here, but not the matrix. So, anyway, so you can actually say that this is describing the configuration of the body. Why? Because this, of course, applies to any point. I didn't say this is a specific point Q. This could be any point. It's an arbitrary point on the body, right? So I can actually forget about the body, because that applies to any point on the body. So the matrix itself, of course, is describing the configuration of the body, right? So it tells me exactly the rotation and the displacement of the origin of my body fixed frame. And I can actually, well, I can actually forget about the body, because kinematically a rigid body is just a frame, right? Because kinematically the rigid body is infinitely extended. Right, that's fine. Now all these matrices, if you multiply these matrices, of course they give you the same type of matrix. If you multiply such a matrix with another matrix, you get again a matrix that has a rotation matrix here, a 3 vector here, a 0 vector, and a 1. So that means we have at least something that is closed with respect to the multiplication. So it's a group, again. But it's also a Lie group. Why? Because first of all we have an inverse, and inverse looks like this. You just multiply and you see that that's correct. Then of course we know that we can introduce smooth parameters for the rotation matrix. This is what we said for the rotation matrices. And of course we can introduce a smooth parameters for the displacement. By just taking displacement itself as a coordinate. So we have a smooth parameterization. We have the inverse that is smooth, and we have the closeness with respect to the multiplication. So we have again a Lie group. And this is what is normally called the special Euclidean group. Well, it's so why is it special? Well, it's special because we have the special orthogonal matrices in here. We have orthogonal matrices R that are orthogonal, and they have to determine +1, right? And again, it's what? It's an isometric in orientation preserved transformation of an Euclidean space, because we still have that preservation of the distance length and also of the right-handed frame. If you transform that frame, whatever the transformation is in another frame, it remains a right-handed frame. You just, I mean, this is what's all about multibody transformation. Well, and there's an identity which is the 4-4 matrix. Okay, fine. What next? You can, of course, maybe write this in a different way, because why do we, I mean, there's no good reason unless you want to multiply the matrices to use these 4-4 matrices, because apparently, I mean, I can forget about the 0 and the 1, because that doesn't give me any more information. I can just write, for example, the configuration of that particular frame, or the particular body, that we call C, bold letter C, denoting the matrix, by just using C, and I use the tuple of rotation matrix and position vector. So you can write the elements in this form. Right, so what about now if I combine these frame transformations? So I have one after the other. So I have like the one frame transformation that transforms from F2 to F1, and I call this C12. I have a second one that transforms from F3, frame 3, to frame 1, and I call this C23. And if I combine them, of course because I was saying I just have to combine, to multiply the matrices, C12 and C23, this one and that one, I get this one. And of course you see what we get. We get, of course, one rotation after the other, multiplication of rotation matrices. But the location vector, position vector, is a bit different. We have the first one plus the second one rotated by the first rotation matrix. That makes sense if you look at what the meaning is, because this one is expressed already in the frame 1, whereas this one is expressed in F2, so we have to rotate. That makes all sense. But there's a bit more of interpretation behind this. And this is, if you look component-wise, you see, if you write the multiplication now using these two tuples, right, of the rotation matrix and the displacement vector, what you see is that you have a bit of an asymmetry in here. The rotations get multiplied, whereas the displacements get like summed up after half of it is multiplied. So what that actually means is that you don't have a direct product, right? Like if you would have the rotations and the translations as a direct product, right? So each collocated with each other, then multiplied, then it would just mean we multiply the first component and the second component, and that's it. But this is different because it's only the multiplication of the first component, which is the rotation, is independent, but the second one is influenced by the first one, right? And this is what we call a semidominant product. What that means is actually that the first group, because we have actually two groups in here, right? One is the rotation group, and the other one is the translation group, right? One is SO3 and the other one is R3. They are not independent. Whenever you have a rigid body moving, right, then of course any rotation has an effect on the displacement of the point, unless the point is actually on the center of rotation. That's behind. And what mathematically is, mathematically we express this by saying that we have a semi-direct product. We will see then later on that this is actually important to realize this and to take this into account when we talk about updates in, for example, integration schemes. Right. And what it says is actually that R3, the translations, of course, have no effect on the rotations, but the rotations do have an effect on the translations. Right. So what about now coordinates? I was saying that we have a Lie group, and a Lie group is something that allows us at least to introduce parameters. And these parameters should be smooth, in the sense that I can differentiate them and so on. And of course, you know that there is this kind of famous, maybe Euler-Rodriguez formula, or just Rodriguez, or just Euler formula, where you come from. And that looks like this, right? So what you do is you fix a rotation axis, a unit vector along the rotation axis, call it E, right? And then you have the skew-symmetric matrix, maybe E hat. Sometimes you have the tilde on it, right? Squirrel on it. I use the hat. So, and then of course you know that this looks like this, right? So you have the sine of phi times E hat, the skew-symmetric matrix, and then the other term is 1 minus cosine phi, and then you have E hat squared, right? So this is the typical form of the Euler-Rodriguez formula. In this case, I'm saying we have a unit vector, and because we have a unit vector along the axis, we need an angle, right? If I forget about the angle, I can actually say, okay, I multiply E with phi and I have a vector whose length is actually telling me how much I'm rotating about an axis, right? So, and this is then giving you this form. So, it looks the same just by taking the phi into E. So, now interestingly, this can be, I don't know how you came along with it. You can, of course, derive it geometrically. And this is probably how, certainly, how Euler did it. But you can also do it in a different way. By just observing that if you take a skew-symmetric matrix, which is not a unit, it's not unit length, so what you get if you take the square of the square, but if you take the cube, if you take it to the power of 3, you find that actually what you get is actually the matrix itself times the square of the length of the vector and the minus sign. And of course you can do this again. If you multiply this again with phi hat, you get, psi hat, you get of course psi hat squared, right? If you do this again, then you get of course psi, but then you have the norm of psi to the power of 4, and then you have plus. And then you can just, collect the terms with the psi hat and psi squared. And then you see, of course, that you have an alternating sign, and then you have the norm of psi to the power of even powers and odd powers. And you put this, okay, then you can arrange it. And what you find then is that this is actually the series expansion of sine and cosine. And this is how you come up actually with this. But having said this, that means like you have this infinite series, you can express this as an exponential. Because this is exactly the exponential if you put these expressions into the exponential, and this is the matrix exponential of the psi matrix. So the conclusion is actually that the rotation matrix that is originally given by the Euler-Rodriguez formula is actually nothing but the exponential of that skew-symmetric matrix, right? So saying that the rotation matrix is actually the matrix exponential of the skew-symmetric matrix that you get by putting in either the unit vector along the rotation axis times the angle, or just an arbitrary vector psi, right? So this is one thing that is at least worth to be mentioned, because now we have something that has to do with the matrix exponential. So we have the rotation matrix, which was in the group, right? So we said this is a rotation matrix, and the rotation matrices form these special Euclidean groups. Now I've been saying that, well, all these, and this is a claim now, I didn't prove it, that this is, that for any matrix, for any rotation matrix, we can find such a vector that we can express it in terms of the exponential. But now what I'm saying is that actually we can express all these matrices in terms of exponential skew-symmetric matrices. So you see there's a one-to-one correspondence between the skew-symmetric matrices and the orthogonal matrices, right? And also, one more thing, we can interpret these vectors that we put into the skew-symmetric matrix, because this is a vector consisting of 3 components, as the rotation parameters. So we have 3 independent rotation parameters, right? And this is the parameterization and the smooth parameterization of rotations. You see, and this is what we have here. And then we call, of course, these small, the skew-symmetric matrices, we can call them, because they are somehow related to the group, right? The group has been like capital S, capital O, 3, right? Special orthogonal group. By tradition, that set that is now called the Lie algebra, that generates a group via the exponential mapping, is just denoted with the small letters. So we have like a small SO, 3. So what we have is the first account of a group and the corresponding algebra. Right? So we have a Lie group and we have a Lie algebra. And the connection is the exponential mapping. Of course you can ask, what is the inverse? Yes, correct, there is a logarithm, but forget about this, it's not so important. Well, anyway, the SO3 in this case is just a set of skew-symmetric matrices, right? That means actually, if you take the transpose, that is actually minus the matrix. Okay, so that is something that leads us to the definition of a Lie algebra. And there are some quotas in here. This is quote-unquote definition. It's not totally strict at the minute. A Lie algebra is just a vector space. So why am I saying vector space? Because of course these skew-symmetric matrices are vector space, right? I can add them together. Whenever I add 2 skew-symmetric matrices, I get a skew-symmetric matrix, right? So it's a vector space. What else? So this, what I'm saying, the Lie algebra is a vector space, so that I get all the elements of the group as an exponential and a matrix exponential in this case of the vector space that I call the Lie group as Lie algebra. So now these Lie algebras, they have special properties, and we will see that we need them later on. One is the so-called Lie bracket. So there is a kind of and we will see this explicitly in a few minutes. But just to make this, because I would like to finish the mathematical stuff first, there is something that is called the Lie bracket. So a Lie bracket is something that is skew-symmetric. So I take whatever that means at a minute. Just bear with me for a while. I have a bracket that takes x and y into the algebra, and this should be skew-symmetric. Skew-symmetric here. So if I commute them, if I interchange the order, so it gives you minus. It's bilinear. That makes sense. And it is closed. That means like whenever I take the Lie bracket of 2 of these elements, it should be still in the algebra. And there's something that's called the Jacobi identity. So you know all this already because you know about R3, the vector space of 3, real vectors in 3 dimensions, and you know there is a scope, a cross product. If you take 2 vectors in R3, you take the cross product, what you get is a vector in R3. So it's closed, right? It is, of course, skew-symmetric. If you interchange x and y, if you take the cross product of x and y, and you interchange it, it gives you the negative, right? That is probably clear. So we can say that actually R3 is a Lie algebra with a cross product. And there's one thing to observe. If you take this skew-symmetric matrix, right? Start here. If you take the cross product of x and y, and you construct this skew-symmetric matrix of that vector that you get out of it, this is exactly the same as if I take the skew-symmetric matrix of x and y minus y and x. So you see, this is a different way of representing the cross product. But now I can actually go one step further, because I know that these skew-symmetric matrices, they itself form a Lie group, which is a different one, which is the one that we call SO3, right? So that means actually there is, again, as a one-to-one correspondence of these cross product and something that has to do with the skew-symmetric matrices. And actually this is what we call this, the Lie bracket in SO3. It's just defined as the matrix curvature. So, good. I would like to come to an end here, and would like to come to the last slide on the mathematics before I finally come to the kinematics. Just something about the matrix exponential. A matrix exponential is very simple. You take the series expansion from an exponential function and you just plug in a matrix. And everything is more or less the same that you know from the classical exponential function. So we have an inverse that exists. We have, of course, this property here. If you take the exponential of the sum of x, for linear, well, a plus b times x is of course the same like taking the exponential times the exponential. It's if the group is commutative, then of course this is commutative, otherwise not. What is important is this property. If you take the exponential of that should be x. If you take the exponential of x and you multiply it from the left with the matrix C, which is invertible, and with the inverse of C from the right, then this is the same like taking the exponential of x left multiplied with C and right multiplied with the inverse of C. We're going to use this later. Okay, so let's come back to the rotations. So I was saying that we can represent the rotation by using a rotation matrix, SO3. Well, probably I can do the same by just say, well, I use my homogeneous transformation matrix, and I have no translation vector there. That gives me the pure rotation again, right? So that is probably equivalent. I make no mistake by using either one. So I know that, of course, that's what we said already, that I can generate this rotation matrix by using a skew-symmetric matrix. I take the exponential of it. Well, I can do the same here. Well, I don't make a mistake. If I put this matrix into my matrix exponential, of course, what I get, the zero does not have any effect. I get actually my rotation matrix here, and everything is fine. So I take the exponential of the 4 matrix, and it only has the non-zero term here, which is the exponential of my skew-symmetric matrix. Why is this important? Well, let's see how this can be generalized. And we know there is a theorem that's called Trance theorem, or sometimes called Mozzi's theorem. You know, different names, sort of the same thing, which claims that any rigid body motion can be represented as a screw motion. Right? So what it means is that we can, for any rigid body displacement, we can find a axis, a so-called screw axis, so that the rigid body motion that takes a body from the initial to the finite configuration is a rotation about this axis that we call a screw axis, and translation of that. Right? And this is what we call a screw motion, because it behaves like a screw. It is of pitch. So let's then see what happens if we do the rotation, the screw motion, and we fix our reference frame of the body so that it is actually with the origin on the screw axis. So this is why I actually was needing this kind of formulation here. So what I get, of course, is the rotation matrix, right? The exponential of my skew-symmetric matrix that gives me the rotation, right? And I know exactly what the displacement is, because I was saying that since we are on the axis, on the screw axis, with the origin is just the vector psi along the screw axis times the pitch, h, we call h the pitch, gives me the displacement, right? So this is correct. Without any further consideration, this is my screw motion that I get if I position my reference frame on the screw axis. And this is the same like saying I take the exponential of the matrix, the format is consisting of psi hat and h psi. Because if I take a product of if I use this, if I use the expansion of the exponential, I get the product. I get the this to the power of 1, of 2, and so on. And the only thing that remains is h times psi. And here we get the full exponential. So that gives me actually a way of representing the school motion as long as I have my school axis on the, or say the other one, if my reference frames are on the school axis. Now what if I have arbitrary reference frames of the axis, that are located somewhere on my rigid body, at a certain location P away, and with a certain rotation. The red one and the green one put a certain relative rotation. So say the red and the green are certainly rotated by r, and the displacement is p. Well, what this means, look, this is just obvious how we can describe this, because what I'm doing is here we have a frame transformation from the right one, the initial one, to the one on the screw axis that I used before to describe the rigid body motion. And then I have the one that transforms back to the right one. This is the inverse, of course, and this is, of course, just a frame transformation. And I can just multiply this, and I can then use my properties that I know. I multiply this out, and find that, of course, r times e psi times r transpose, this goes in here, and the rest gives me this. And that's pretty simple. And then I use the property that I was mentioning, that if I multiply from the left to the regular matrix and with the inverse from the right side, I can raise this into the exponential of the argument of the exponential mapping. Then I can actually say, okay, I can redefine this term here, and I can call this psi prime, right? And I have a new vector actually, and this is the vector, because this is nothing but rotating psi. That is defined, psi prime is just the rotated vector psi, rotated by r. And then I get finally this this rigid body motion, this homogeneous transformation matrix that defines the rigid body motion. Okay, this is one possibility. The other possibility is that start again from scratch and say, well, of course I can do the same, but now I can actually say, I know that this property that the one that I'm using all the time is that if I multiply from the left with a certain matrix and with the inverse from the right, I can put this into the exponential. I can actually do the same with the four matrices. So I can actually take these matrices, this and this, into the exponential argument. I multiply this, and then I take the exponential. What it means is then that I take the exponential of this psi prime, right? Because this was the one I have just defined before. So I take the exponential of psi prime, which is the rotated psi, and a certain v prime, which is just given here, which is what? It is the cross product of p, the displacement vector, to the screw axis, and with the axis psi prime, and then we have a certain term that has to do with the pitch, that gives me the direction along the screw axis. So what I'm saying is actually that if I have an arbitrary reference frame, the exponential mapping that gives me the corresponding screw motion is actually the exponential mapping of this 4-4 matrix. And these elements in here are the screw coordinates of a general displacement, of a general screw displacement. And this eventually gives us the general form of the exponential mapping on SE3. The exponential mapping that gives me the finite screw motion corresponding to a screw axis given by psi, which is the unit vector along the screw axis, and which is a certain p away from the origin of my reference frame. right? So these are the general screw coordinates. I'm not sure if Dimitar introduced it before. And maybe remember that if you just forget about the pitch, then we have the Blücher line coordinates, right, that define a line to this point that we measure in a distance of p. So the conclusion is now, I mean, the result is now that we have the exponential mapping that takes screw coordinates corresponding to the screw motion and returns the corresponding finite displacement. Right. And of course, how do you construct it? Just to repeat it, you have the screw axis that the screw motion corresponding to motion about the screw axis. You take the axis psi, and then you take a displacement vector for the q. The cross product goes in here. The first is the angular part, the second one is the displaced, the linear part, and then you have your screw coordinates, and this goes then into the exponential. Now we have we have like 3 steps at the moment. We have first of all the screw axis, then we construct this 4 times 4 matrix, this one here, that goes into the exponential mapping, right? So you might call this x hat again, right? So we take psi hat, and then we take this eta that we just defined as the cross product, and then this goes into the exponential mapping. Well, why not give it a name? Why don't we say that we call all these 4 matrices with this skew-symmetric matrix and the linear vector here. Why don't we call this SE3, as we did for the rotations, for the SO3? You can just say, well, this is actually a vector space, right? If you take the sum of it, you get the same sort of matrices. But this is the one that gives you the SE3 matrices, the homogeneous transformation matrices, by means of an exponential mapping, which was the kind of a definition of the Lie algebra. So essentially what I'm saying is we have now the Lie algebra to the Lie group of rigid body motions, right? And I was saying that the Lie algebra has properties, and one is an operation which is called the Lie bracket. Again, in this case, the Lie bracket is just the matrix commutator. You might have seen this before. This is nothing but the screw product. I'll come back to this in a minute, where we really need it. Okay, and yes, so essentially to sum up, if we return now to the change of reference frames, then we can say if you have a certain screw coordinate, psi x, eta x, and you transform to a different reference frame, where the reference frame is either rotated and displaced to a certain other reference frame, then the screw coordinates in a new reference frame, so this is given by the frame transformation, and this goes by actually transforming like this. Because if you put this all in a matrix, then you see that you take the original ones, psi eta, and then you get the psi prime, eta prime in terms of this matrix, this transformation matrix. And this has a certain name. And normally it is just called the frame transformation matrix. Sometimes it's called the motion tensor. In some people in flexible multibody it's called as the motion tensor. In Lie group theory it's called the adjoint mapping. Why is it adjoint mapping? Because see, this is an element in the group, right? But it acts because this is an element of the algebra. So this is like a group element acting on an algebra element, which is normally called the adjoint action on the adjoint mapping. Good. Now finally make an end to all this maybe abstract things and come to the real kinematics. Just to summarize, of course, rigid body motion can be described or is represented by these 4 matrices, which normally called homogeneous transformation matrices. We call this SE3 elements. SE3 special Euclidean group. So what it does actually, if you start somewhere from your with your rigid body, you have a reference frame on it, then and if you perform a certain screw motion or a general motion, then this C, the SE3 element, is telling you how this frame is actually configured with respect to the original frame. And you can express this by assigning a screw axis, psi, at a certain displacement, and we know that the exponential mapping takes care of it, and we get C as the exponential of these co-coordinates that we can define in this way. And this co-coordinates itself can be transformed from one frame to the other by this frame transformation matrix. Okay. Now finally the kinematics of the serial chain. This is much more interesting. So that was one body. What about now we have a chain? So we have a kinematic chain, we might have a serial manipulator, we have a closed chain maybe, but look at an open chain in a minute. Of course we have many bodies, right? We have a link, we have many links, maybe we have n links. Say that we have, we look at body I or link I. So of course we can fix a reference frame. So kinematically the body, the link is represented by a reference frame. Put a reference frame on it, then of course I have a space fixed reference frame. This is my global world fixed reference frame. With respect to which I'm actually able to describe the configuration of all the bodies in my chain. And I can of course do the same with the second, maybe the predecessor if I have an open chain. So I might have link I minus 1, link I, and in between they are connected by a join. So we just call it join I. Okay, join I connects link I minus 1 with link I. Of course I have a joint angle, call it QI. And what can I do? Well, of course I can maybe associate a certain screw axis. Because if I have a joint, then the joint performs a relative motion. By, as we know, any motion could be represented as a screw motion. So I can associate a screw axis to the joint. Apparently I use the simplest case, which is a doublet joint. There's an obvious screw axis, which is the doublet, the axis of revolution. What can I do then? Well, say that I have my CI. So CI is the relative configuration of the link I with respect to the space fixed frame. I can say, well, I can of course have, indeed, I have the configuration of link I minus 1, that has the same structure, right? So I can say, well, I take my configuration of Ci minus 1, and then I follow up with the relative configuration of the two bodies, and I have the configuration of link I. So I have Ci minus 1. So what I'm going to do is, I take Ci minus 1, the configuration of link I minus 1 with respect to the fixed, world fixed frame, followed by a constant transformation Bi. It's B for body fixed, constant transformation from Bi minus 1 to Bi for joint angle equal to 0. Why I'm saying equal to 0? This is my reference configuration. So if I say my joint angles, my variables of the joint are 0, then I should observe the relative configuration Bi. Good. And then I have the one that has to do with the joint motion. I mean with the actual variable joint motion. And that of course I can describe by an exponential mapping. I just take the exponential mapping of what? Of the SE3 matrix that is associated to my screw axis of the joint. But the screw axis is now expressed in the reference frame on Bi. Okay, does it make sense? Again, so I start from Ci minus 1. Then I have the configuration of that frame with respect to this frame. Then I have this Bi. Bi is a constant transformation from this frame to this frame, right? So what happens if I'm moving, if my joint is moving? Then I'm still moving relative to this frame according to my screw axis. So I'm actually expressing my screw axis in this frame, take the exponential, and I get the relative motion of that thing, right? So that goes in here. And you get, okay, so that's kind of, anyway, so it says, when I talked about this, the joint screw, there's only one characteristic here. The joint screw coordinates are then like this. Well, this is just the displacement vector, here, displacement vector, and of course the unit axis along the joint axis. That's fine. And of course I can make this repeatedly, and I can just start from the very first link and go all the way along up to my link I. I just make recursively the relative motions, and summing up, or say multiplying up all the relative motions of the links gives me the motion of my terminal body, or whatever it is, bi, right? And that's fine. And you see this is a very compact way of expressing the relative kinematics of kinematic chain. And this is normally called the product of exponentials. That makes sense because we have a product of exponentials. Now that's not totally correct, because we still have this b's in here, right? But there is actually a way of getting rid of the b's, because we can express it in this form. And that goes by the same argument. Instead of using this body fixed reference configuration, what I'm doing now is I forget about the reference at a minute. Just say that we start with reference 0. That means I'm actually considering what happens to a frame attached to, say, body. What can we do? Start with body I. So say I'm looking at body I. So nothing is moving except joint I. So body I is moving because joint I is moving. What is going to happen to a frame that is attached to body I, initially coinciding with the space fixed frame? Well, it's very simple what's going to happen. It's that. It's the exponential of this screw coordinate, y, I, the one here, expressed in the space fixed frame. Because this gives you exactly the relative configuration of a frame here, initially coinciding with the space fixed frame, according to the joint motion, right? So if this one is moving, then we take actually the frame out of the initial frame. So we have that relative motion, right, of a frame that is attached to the link I, but initially coinciding with the space fixed frame. And we can of course do this with all the things. The only thing that is missing is that of course normally my frame is not initially coinciding with the space fixed frame, but it's somewhere. And this is why we need the reference configuration, which we call AI, so the absolute configuration, AI, that gives you the configuration of the link frame I for joint angles all 0. The same thing, but it's even more compact. See, the only thing that you need here, you can even, maybe, if you are not interested in, most of the time we're not interested in body fixed reference frames, you can even forget about AI. The only thing that you need here is the y1 up to yi. And these are the screw coordinates of the joints relative to the space fixed frame. See, this is a very compact and very easy way of representing the kinematics of an open chain. Because the only, okay, I'm repeating myself. The only thing that you need are the screw coordinates in the reference frame, in the global reference frame. And there's of course a relation between AI and all the bi up to b1 up to bi. That's clear because if you put in q equals 0, then of course what you get is this is ci is then ai, but here is the product of b1, b2, and so on. Right? That's clear that we have that thing. And this is another one which is just saying that again we have a frame transformation. We're transforming actually the body fixed screw coordinates into the space fixed screw coordinates. Because what aj does, it actually takes from the body fixed coordinates in the initial configuration into the space fixed coordinates. Right. So we have actually two ways of describing the configuration of a body I or link I, in an open kinematic chain, either using the global reference frame. So all the joint coordinates, sorry, the joint screw coordinates are expressed in the space fixed frame. So we don't need body fixed reference frame, we don't need body fixed joint frames. We only need one single reference frame. That's good. The other one is the one that is normally used in for some multibody dynamics, is that we have body fixed frames. Two things, both have pros and cons. What is important? Okay, so this is nice because we only have one frame. This is essentially, okay, so why we need this then? Well, because you know about Denner-Hartenberg parameters, for example, right? Denner-Hartenberg parameters are what? They're describing your local link geometry, right? So what I do is actually they describe the B's. Number one. Number two, if you want to optimize a system kinematically, what you want to do is probably to tune, to tweak your geometric parameters, the link parameters. And they are encoded in the B's. That's number two. Number three could be kinematic calibration. And actually there are nice papers actually on kinematic calibrations. And they use, of course, these body fixed things. But what they do is actually the following. They say, well, if this is a rigid body motion, well, it's a constant, but it's a rigid body transformation, right? The B's are still these SE3 matrices. Then, of course, I can represent them as an exponential. But I can say that this B, right, the B1, BI, could be an exponential of maybe UI, something, right? Whatever the name is. So, like Q times X, I could say this is maybe pi times U, right? What that means is that I have actually a parameterization of the link geometry, right? And there are nice algorithms that use the exponential formulation. They call it local product exponential so-and-so formulation for kinematic calibration. Because you only have to tune the parameters that are in the exponential mapping that is giving you the B's, so to adapt to your measurements, for example, if you identify the kinematics of a manipulator, right? Okay. Of course, yeah, there is one, known application, but this is for kinematic mapping, so that you have, for example, a manipulator and a serial chain, and of course, then you get the end effector configuration by, by the product exponential. Good. I skipped this example. It's normally nice to see a practical example, but I don't have time. Right, just let me say about the subgroups. I know that the next presentation will talk about subgroups, but you probably know that, or you can at least imagine, that instead of looking at the six-dimensional, the spatial transformation, there are many what we call subgroups. Subgroups means, like, for example, you have planar motions, right? So planar motion is one that has three dimensions. But there are spherical mechanisms, for example, so we have circular motions. And these correspond to subgroups, and there's a nice thing that all of these so-called lower pairs, or Rayleigh pairs, they correspond to a subgroup. Maybe later on the talk that talks about this. The universal joint, the hook joint, for example, is not subgroup. Okay. What about our velocity? Well, of course, you know, without going to any sort of Lie groups or something like this, that you can express the velocity of link, say link K, in the chain. For example, in two ways. You can express it space fixed, or you can express it body fixed. If you use the space fixed, what I'm going to do today, simply because that's what we are normally using in mechanism analysis, is what? The idea is to say we have a space fixed frame, and then the velocity or the twist of link K in the chain is given by pure vector algebra. So, you know, the angular part is just to take the joint velocity, the q, angle dot, which is q dot, times the unit vector along the axis, gives you the omega. The omega caused by this joint, right? To this joint. And you sum them just up, you sum them all up, and then you get the total omega. That's fine. The linear part is very simple. You just take the cross product of the displacement vector times ek times the time derivative of the angle. But what exactly do you get? That's a linear velocity, right? But what does that mean? This is the linear velocity that gives you actually what? This is the linear velocity that you measure at that particular point, at the origin of the space-fixed frame as if the body K would be traveling through this point, right? And do the same for k minus 1 and k minus 2 up to 1. And then you sum this up. So essentially what you get is the space-fixed velocity, but the space-fixed velocity is not just taking the body-fixed velocity, transforming it into space-fixed frame. It is the velocity, the linear velocity of a point on the body, k, that is momentarily coinciding with the origin of the space-fixed frame. Right? It's a bit of a tricky definition, but that's what you normally use. Okay, so that's clear. That there's no Lie groups, there's nothing in here. But we can of course define it using this Lie group things. And this goes like this. If you just look what happens if you take C dot and multiply it with the inverse, you get this. And this is exactly what I'm talking about. R dot minus, this is omega, right? This is omega hat. This the cross product matrix. Essentially this is omega hat. This is like omega cross R, right? So, and this is essentially what I was saying. This is the space-fixed velocity that we measure here. So there's a different way now of the one here, right? So this is a different way of defining the space-fixed velocity. But in this case, you get this space-fixed velocity encoded in this 4-4 matrix. The one that we call actually small int3, that we said was belonging to the algebra, right? So this is a different way. But you will see this is a nice way of doing it because it pops up later on in several instances. So, okay, so this was the definition for one body. What about I have a chain? So I have a chain. So my chain, of course, has the configuration of the chain, of a body K in the chain. I was saying that you can express this by the product of exponentials. So I have my exponential, I mean the exponential of y1 and then times up to yk times the reference configuration. So if I just take this term, put it into the definition now that I was just introducing for the space-fixed velocity, what I get is, of course, well, I have to take the time derivative, right? So I know that c depends, so what is time dependent here? Y is constant, because these are the constant initial, the constant school coordinates in reference configuration, right? The only thing that is time dependent are the q's. So, of course, what I have to take is the partial derivative with respect to q, and I multiply with q dot, right? So this is what I have here. Now just do this. Just look what happens. Take the q dot. Take the q dot, and then you see that we have somewhere in here, you take this is the, you know, the, say that we take q partial derivative with respect to qi, somewhere in the middle. So we have the exponentials up to qi. Then we have, and this is a property of the exponential, is that if you take the if you take the partial derivative of the if you take a partial derivative of an exponential, a matrix exponential, and in our case we have yi qi, right? If you take the partial derivative with respect to qi, then what do you get? Now you have to remember this is a matrix exponential. So, you know, if you take the normal exponential function, it is just the exponential function, right, times yi, right? Now the question is, because it's a matrix, does it not go to the right or to the left side? Well, it actually doesn't matter. It's both correct. So, right. So this is what goes in here. So this is what we have in the middle, right? And then we have the inverse. So, okay, 1, then we have the yi, and then of course yi plus 1 and so on. So yi plus 1 cancels out because we have the inverse that goes from yk up to y1. So the only thing that is left is, of course, the one that are not cancelled out, but it's the one from I down to 1. So we have the same on here. We have 1 up to I. And you see that essentially we have to think that we have been calling before the adjoint method. Right? Remember this one when we talked about the frame transformation? This is what we call the adjoint action. Okay, conclusion is that actually the partial derivative times the inverse that I call SI now for the instantaneous screw axis of joint I is just given by the frame transformation that is described by this adjoint mapping acting on the reference screw of joint I. Okay, so what I'm doing, actually, I take the yi, the one here, is the screw coordinate of joint I in the reference configuration for joint angle equal to 0, right? So this is when we have, so this is the reference configuration. What is this doing here? This is the exponential y1 up to yi. This is actually the configuration of frame I, if you forget about the reference configuration. This is actually the motion of frame I. Remember that it's like this one here. If you forget about this AK, essentially this is CI. So what I'm saying is actually this transforms the screw coordinate of joint I in the reference configuration into the actual, in the instantaneous, in the current configuration of the chain, as it is moving according to the joint angles Q1 to Qi. Right? So, and the whole thing actually sums up to the spacious Jacobian. Because we can, of course, put all these columns, because we have these two coordinate vectors, these are 6 vectors, we put them all in the matrix, and this 6 times n matrix is what we normally call the Jacobian. It is sometimes called the geometric Jacobian because it consists of these geometric entities, right? And the instantaneous screw coordinate vectors are nicely given by just the frame transformation according to the chain. See, this actually is the motion of the chain from body 1 up to the joint, right? This is the screw coordinate of joint I, and this is the chain. Actually, this describes the motion, the current motion of the chain up to joint I. So actually, it's just, you know, describing how the joint screw coordinate is moving as the chain is moving. Okay. Yeah, just one, just saying. Good. What about accelerations? Because we talked about velocities, right? What about accelerations? Take the time derivative. What about jerks, jumps? I mean, higher order. If you take higher order derivatives, it's important, and there is a kind of a history behind this. And if you look at the papers, I mean, Harvey Lipkin talked about this, also Karl Wohlert talked about this already, and nice paper, which is not so actually well known, is by Jean Lervet in the Journal for Applied Mathematics and Mechanics. Nice paper, would recommend reading it. But also, if you look then at the the school of say the colleagues of Rico, Jose Rico and this Mexican school, if you read these papers, if you try to read these papers, it's not easy. They did a good job, but they tried to come up to the 4th or 5th order, 5th time derivative, right? It's getting very messy, very messy. But at the end, it turned out that there is a systematic way of doing it. There are just 2 recent papers, and I would like to give you an idea about this. This is probably not for after lunchtime, but you have it in the PDFs. It's all there. Essentially, you start by saying, well, take V dot. So V dot takes, of course, well, this is clear, so the chain rule, right? And then we have to take J, the Jacobian time derivative. So and this is a bit tricky, because of course the Jacobian consists of all these screw coordinates, SK. How do we take this time derivative, the screw coordinates? Well, again, we have to take partial derivatives. So, again, now let's say that we have the original version of the adjoint mapping. So we have that particular version that we just derived, right? So what we have to do is we have to take the time derivative of all these things using the product rule, or the partial derivatives of these. So say that we are here. So we have to take the time derivative of this thing, this is constant, and maybe this one. Okay, so this time derivative plus this one. Well, then you say, well, time derivatives, or partial derivatives. So there is j between 1 and I, because there is, they only depend between 1 and I. Okay, there is then the 1 ji here, j upward, yj. So yj here. And then we have we do the same trick that we did before, and then we find that the yj pops up somewhere in between. What can we do now? It's not so nice. It goes from 1 to j, right? Then it goes from j plus 1 up to I. What about saying, I don't make a mistake actually if I say, well, this is fine, this goes from 1 to j, this is j. What about saying I just insert now minus j up to, or down to 1, and then I have, so this was the inverse, right? And then I go from 1 up to j, and then up to I don't make a mistake. What remains is actually the 1 here. Because you see, the only thing that, because this cancels out, right? J is less than I, so the j is less than I, the only thing that remains is j plus 1 up to I. So this is correct. I'm not making any mistake. But what I'm doing here is I have 1, j here, j, 1. So you can identify actually that this, what we have here, is just what? This is actually S. I'm sorry, this is actually Sj, right? Do the same here. So we go from 1 to I, we have the I in the middle, then we have I to 1. And this is essentially Si. Do the same here. We find actually Si, and we find Sj. So we have seen this before, right? Because we have this SE3 matrices here. So we have 1 times the other minus this one times this one. That's what we call the matrix commutator. So what I'm saying is actually, of course, the index range. What I'm saying is actually that what we get here is the Lie bracket. Because we said this matrix commutator was the Lie bracket in SE3, right? So the result now is that if you take the partial derivative of S, the instantaneous screw coordinate of joint I with respect to the joint J, or J less than I. It makes sense because the joint has to be before the joint in the J, otherwise it doesn't have an effect. Then it's just the Lie bracket of the two screw coordinates of joint I and J. And remember that what we call Lie bracket and so on and so on. It's just this thing. It's just what is normally called the screw product. It's just simple vector products, right? You take the vector product of the angular part, and then you have this kind of mixed vector product here. Totally simple, purely algebraic. So you get the partial derivative in terms of a very simple algebraic expression. Of course, you can, if you formulate this in vector formulation, then you have just, instead of the cross product matrix, you have something that you could call the screw product matrix, right? And that's fine. So it looks like this. So you see, this is a very interesting result that is not so new, but it's important that, you know, we understand the way in which we get it. Why? Because it allows us to come to the next order, to actually take the next time derivative. Why is it now so easy? You see, the only thing that we have to accept is this. So we have shown this, it's fine. We know that the Lie bracket is bilinear. And of course, the derivative operator is a linear operator, right? So the only thing that I have to apply is, of course, well, just the chain rule, right? And the product rule. The Lie bracket being bilinear leads to this. And of course, this is what we know already, because you know that this is again the V bracket, right? So essentially, we get this kind of thing. So it's very simple. So, and what we get at the end is, of course, the acceleration. See, the acceleration, if you look at this, it looks very compound, right? Now, imagine that you want to implement it, that you want to write the code, you would like to, implement this in a computer. Normally, if you try to implement, acceleration analysis and maybe jerks and so on, that becomes a bit messy, right? And prone to errors. If you implement this, that's totally simple. And you can, of course, go further, and then you have the third order. You might need this for sensitivity analysis. If you, for example, in dynamics, if you want to linearize your equations, then of course you have to go to the next level of partial differentiation. Right? Your motion equations are second order, so you have to go to the third order. If you want to optimize it, if you want to optimize the system, you need again partial derivatives with respect to the joint coordinates. And so you have the third order, and of course you go to many, whatever you want, right? Good. I think I'm almost done, but I would like to at least look at something that is important. There's something that is sort of invariant, and this is the kind of motion space associated to a chain. So now, given that you have a chain, an open chain, how do you characterize the chain? I mean, in terms of motion. Well, we can say we have so many joints, we have so many types of joints, but how are they located? How are they arranged? What is actually the motion that this chain can perform? Is that kind of a conservative estimate for the motion range, for the workspace, if you want to say, if you have an open serial manipulator? And this goes like this. So we know that instantaneously, this is the vector space of I'm not saying end-effector velocities, of the velocities of body K, right? So, yeah. So this is the velocity of body K in the chain. This could be the end effector of your manipulator, that's what I'm saying, end effector. So the span, the linear space, the vector space defined by these screw vectors is of course the vector space of possible velocity of the body K. So there's a thing, there's one result that says if you, and remember how this was defined, the instantaneous screw coordinate, right, of joint I is the adjoint mapping of the exponential product 1 to I applied to yi. So there's a theorem that says if you have this kind of expression, that you have an adjoint matrix that applies actually an exponential to a vector, simply speaking, then this is given by this Taylor expansion. So if you apply this here, then what you see is actually that you get the SI is actually given in terms of Lie brackets of yi with all its predecessors, with y1, yi, y2, and so on, right? So now, this is interesting. Remember this, the cross product. If you take a cross product of two vectors, so the maximum that you can get is, of course, a 3 vector, right? What about if you take screws? Like if you take a screw that corresponds to a planar motion, the maximum that you can get is again a screw that corresponds to a planar motion, right? If the system is only moving in a plane, it cannot go anywhere out of the plane. So that means actually what I'm saying is that this is kind of defining a closed system, what we call normally the complete, say the involutive closure of a system of screws. You can imagine that we are looking at a finite dimensional algebra, right? So we have these vectors, and these vectors define a certain finite dimensional space, simply speaking, right? Now I'm taking now these Lie brackets. Now these Lie brackets, they give you something that might not be in the space. But at least there is a limit, because we are looking at the linear, at a finite space. So this will terminate at a certain level of, at a certain iteration step, right? Because you iterate all these lubricants. So, and this, what we get out of this is actually, we get a Lie algebra. Why? Because it's closed by definition. Because you take all the brackets and they are closed. If you then just look at this set of whatever you get at the end, this is closed, right? So we have a Lie defined by these Lie brackets. And since these are these group coordinates, this is actually, this can be shown, just believe me, this is actually giving you the space of, let's say, the smallest subalgebra of SE3, like of the motion space, right? Of the motion group, that comprises the velocities, the velocities that are possible to generate for this body. Of course, corresponding to velocities are finite motion. If you take the algebra, take the exponential of the algebra to gives you actually the corresponding group. And I would like to skip this maybe. Good. Just mentioned. I mean, the point is there are so many things to discuss, but the time is not enough. I have some examples. If you're interested, I have mathematical examples, so you can really look at the examples. But I would like to just go and, if you're interested in dig deeper into this. Right. And this, of course, has to do with the workspace, right? Good. Good. Closed loop systems. And I would just briefly mention closed loop systems, then I'm done. What's the difference between an open and closed loop? Well, a closed loop, of course, has to satisfy certain constraints. Just briefly. So what you can imagine is that we have this mapping, right? So we have the product is exponential. If you say that this is a closed loop system, then of course what we have to assume is then, if we are doing it properly, that if you define this, you have a chain consisting of link 1 up to link n. If it's a closed loop, the link 1 and the link n should coincide, right? That means, like, if I evaluate my product exponential formula, this should be the identity. That means, like, the vectors of joint coordinates, joint variables like angles, that are allowed, that are satisfy my loop constraints, are those so that this product of exponential gives the identity. That kind of makes sense, I guess, right? So, and this is defining your configuration space, right? Now, this configuration space is, in this case, an analytic variety instead of an algebraic variety. It's like yesterday, this morning, I think yesterday. The only difference is that now we are looking not at polynomials, we're looking at this kind of analytic function like sine and cosine, exponentials, and so on. Right, but the interesting point is how do we, what can we say about this variety? And is it not possible maybe to say something about the mobility? Because what is the mobility of a system? The mobility of a mechanism is the dimension of its configuration space, right? That's clear. I guess. Good. And but of course they can like the forward mechanism. You know, it's one degree of freedom. So essentially what we have like how many? We have 4 joint angles. So we have a 4-dimensional space, and there's a curve, right? I mean, the configuration space consists locally of curves in the 4-dimensional space. If you make a section, like this is a 3-dimensional section, you see there are curves, but they're intersecting. And these intersection points are the singularities, right? Now, wouldn't it be nice to have a method actually to analyze locally what happens at the singularities, or even in regular points? And this, of course, we can do because we have this, what I've been showing, this way of higher order derivatives, because you can using these kind of higher order things, you can approximate locally how your configuration space looks like. This allows you, of course, to analyze what happens at singularities, but also you find mobility. It's a different way of finding mobility, because identifying mobility is still not such an easy task. And now there could be one question: what is maybe common to all these mechanisms, or what is different? Well, common to all these mechanisms is, no, maybe not this one. Forget about this one, but common to these mechanisms is they have 4 Lagrange joins. But maybe this is the only thing that is common. This is a Bennett mechanism, right? So, but there's something in common here. These are spherical mechanisms, right? They can only move. You see the joint X is intersecting at this point, and this is a special case. They are intersecting at infinity. So they satisfy certain properties, but these have to do with the motion space actually of the chain. So what I'm talking about is that if you look at, for example, this well-known Chebyshev-Kurzbach-Rubler formula, there is some magic number always in here. You have the 3, you have the 6. Well, there could be maybe some more. Essentially, it could be 1, 2, 3, 4, 5, 6, not 5. Why? Because what that number, the magic number, sometimes it's called G, sometimes it's called the characteristics of the chain. What it actually is the dimension of the loop space, of the motion space that we can identify by looking at the V brackets. Essentially, this is the dimension of the subgroup corresponding to the motion group. In this case, it's the planar motion, right? So the planar motion is 3-dimensional, right? The spherical motion, again, is 3-dimensional, and so on and so on. But what is behind this number is essentially the motion space, the subgroup, and this is why there is no 5. Well, by the way, I have no CF1, but it doesn't make sense, but it could be. Yes. And you see, that's fine. And the interesting thing is that this is, of course, inherent to the system. That means even if I open it, I still have the same motion characteristics, right? And this is because, of course, the loops, the motion space of the chain is invariant, of course, with respect to the chain itself. There's been a problem. It is called Quaternions formula. I think we know all this. And it goes back to, there's a nice classification which is quite disputed. I don't like it either, but it goes like saying that it's a mechanism where we can just identify the loop space. I mean, the algebra is called trivial. If you can use it to identify the mobility, it's kind of exceptional if we have to do intersections of algebras. Like here, you can identify that there is one planar motion here, right? There is one planar motion here, and then the platform is actually bound to the intersection of this, right? So, well, since we can conclude the mobility by looking at the intersection, someone called this, and this was actually in a way exceptional, and if we cannot do anything, it's called paradoxical. Of course, this is not a good classification because it does not classify the mechanism, it just classifies the ability of looking at it. Okay, and that is almost it. I would just maybe say one word about this, that we can actually, by looking at the D brackets, I mean the closed form for the higher order derivatives, we can identify the local shape, not the local structure of the configuration space. Like here we have this singularity, but we still have a way of identifying that this is a bifurcation. And it's interesting that if you look at the FIFO mechanism, that is a cone. It's a ring cone. It's a 2-dimensional cone that we can identify. Okay, good. I think I should stop here and would like to just thank you for the attention. If you have any questions, I was just, trying to dig something. If you're interested in any of these topics, I have many slides on this. Just let me know that we can talk about it. Thank you.
Let's take about 5 minutes, and in which feel free to ask questions, and we can do
temperature changeover, and we can have bathroom breaks needed. And then 5 minutes from now, meaning about 5 minutes till 4, we'll start with Dr. Kumar, and we'll try to finish by around 5:30 so that we can get to dinner and get a lunch on that.
This is before we were in the lab. Ross Hattie was playing around with similar math and did a course that was supposed to be from a book they were writing. I don't know what happened to it. Is the Ross and Howie, where they did a similar derivation of the velocity of serial chain. The difference is he went on. So this was probably mathematically more elegant.